Hello, welcome back to Studio 68. I'm Bill Slusser, and we're ready to do some Q&A. You might recall in our last webinar, Do's and Don'ts of Lightweighting Glass Containers, we had a number of questions come up in our chat. We didn't get a chance to answer them all, so we're going to take some time right now and go through some of those questions with you. The first question we have: how are design parameters like internal pressure and impact strength values decided for returnable beer bottles, particularly 650 beer bottles? Well, let's talk a little bit about that. When it comes to setting our design factors, we're going to want to use real data from what the bottles are going to experience. Now, when it comes to internal pressure, we're going to specifically want to know things like the carbonation level, the expected temperature range, and the duration that that bottle will be at those temperatures. For instance, the pasteurizer has a relatively high temperature, and commonly the amount of time is about 20 minutes. On the other hand, for a load like impact, as I mentioned in the seminar, the best way to make sure we have the right number inputted into our design analysis and set those parameters is to do an impact survey measured with a shock logger, and that will give us real numbers. So those are the kind of things we want to do. Good data in is going to give us good data out, and we'll be able to do a nice FEA and allow to set those maximum allowable numbers. Next, our second question: is there a minimum thickness for lightweight wine bottles? Well, the thing we need to understand here is that every single design is unique, and it's going to be dependent on the loads that we're going to place on that container. So we talked about it. We don't want to use the constriction of a minimum thickness specification when we're doing a lightweighting project, because that may hinder us from being able to do as much lightweighting as we possibly could. However, if we use FEA intelligently, and we're taking a look at where the stresses are acceptable and unacceptable, we'll be able to know what kind of thickness we can get to when we do the FEA to ensure that everything falls into the acceptable range. We're going to need to know those load levels. We're going to need to know specifically what we're going to ask that bottle to do. But other than that, those thickness specs will fall right out of our FEA analysis. All right, question number 3. Are lightweight bottles more susceptible to glass breakage in the event of inclusions present within that glass lot? Well, the first thing I want to say here is that when we do a design analysis, when we are assuming that we're going to manufacture this bottle, we're going to assume that it's made in the absence of flaws, checks, inclusions, infolds. We don't assume that those will be put into the bottle. We're going to use good QA procedures. We're going to use good manufacturing practices that we talked about to make sure that quality is high. So we don't really want to put the assumption in that we're going to use a bottle with an inclusion. Now, let's be frank about the situation. When we take glass out of a lightweight container, it's going to, of course, experience a little more stress in certain regions. If we do have an inclusion, like a stone or a seed, within that region, the stresses are going to be higher. That seed is going to reduce the surface strength, and we could have more issues with it. So, in the end, we want to make sure that we are aware of the fact that those lightweighted bottles are a little more sensitive to the flaws, but we have to make sure those flaws are not present. Now, one of the resources that we have available for you, particularly for things like the inclusions of stones, is we've got a book, Color Atlas of Stones and Glass. It's going to help you identify the nature of that stone, which means you've got a better chance to rectify that in future runs. Question number 4. What are the safe stress levels in megapascals that we should look for while doing FEA for non-returnable and returnable bottles? Now, we did touch on this a little bit in the seminar, and maybe it was the basis for this question. But we need to know a couple of things, and it goes back to what we talked about in the fracture equation. Now, your question refers to what tensile stress levels are acceptable. I'm going to answer that question by taking a look at the glass strength portion of that equation. We need to know how we're going to use that container. It comes down to the surface condition. Well, the difference between an NR bottle and a returnable bottle is that glass surface strength, particularly on the outside. As we use that returnable bottle over and over, those glass surface strengths reduce, and we talked about that asymptotic strength level. When we do the FEA, we're going to know those strength numbers. We're going to input that into the program and be able to then determine how much tensile stress can this thing take? And that will set the level. Again, specific to what loads we put on that container, how that bottle is shaped and designed. So we have a uniqueness for every bottle, but it's all going to be dictated on our knowledge about those glass surface strengths. Question number 5. What is the best approach for a true new design for lightweighting in the initial design? Well, in this particular case, we like to consider this similar to what we refer to as a conceptual design. And in a conceptual design, you can start very much in the imagination phase. You can just decide, generally speaking, even from a sketch, what you might want to have from your bottle design. And from that, we can work with you. And from that perspective, we'll go to the designing phase. Now, there might be some constraints, and you can think of these dotted lines that we have on here as some of the constraints you have. Maybe it's the size of your filling line, maybe it's the cases, but you're going to want to have some general sense of the size that bottle has to fit in. Once we come to a conclusion of where we're going to be, and we do that with an eye towards lightweighting so that we make sure that we're using as little glass as possible to achieve that shape, we're going to take that into the FEA stage. And once we've looked at the stresses that are present, as you remember from our other discussions, you're going to see areas where stresses are higher, and we're going to make decisions whether or not those stresses are acceptable or unacceptable based on those surface strengths we've been discussing previously. Consequently, we'll be able to decide and or make changes to this design to ensure that it's in the acceptable range, and then we'll probably then take it on to a final decision point with the customer, in which we can actually create a model of that bottle. It could be acrylic. We can give you technical drawings. And we're ready then to take this to the manufacturing state and do some testing on those bottles to make sure we get all the way to a very comfortable level, that we are confident that bottle is the way you want it to look and it's going to perform exactly the way you want at the lowest possible weight. Next up, question 6 is asking, borosilicate glass has more strength to weight. Why are we not using that for regular container glass? Well, there's a number of reasons. The first thing we want to realize is that when it comes to borosilicate's strength compared to soda lime silica, that's usually found in a theoretical laboratory setting. But in reality, when it's out in actual use conditions, and as both bottles pick up damage through handling, they're going to pretty much end up at a very similar surface strength. And consequently, the differences, the advantages that we might have with borosilicate aren't really realized in performance. The other thing we need to realize is that when I add boron to the batch, that is an expensive additive. It also raises the melt temperature considerably. And so consequently, we're going to be looking at very high cost to make a borosilicate. Now, borosilicate has its place, of course. We see that when it's in things like pharmaceuticals, because as a pharmaceutical, borosilicate is not reactive with the product, and consequently, that's something that's desirable. We also know that borosilicate has low thermal expansion characteristics compared to soda lime silica. Consequently, we get good thermal expansion resistance. So things like a Pyrex in your labware is great use of borosilicate, or possibly cookware. Those instances, it's justified to have that higher price. But in our everyday soda lime silica containers that we put beverages in, that additional cost is not justified. All right, question number 7. During pressure tests, the main breakage that they're seeing, this particular individual, is in the heel area. And they note that on slide 17 of my previous webinar, the do's and don'ts, the distribution of pressure stress is low in the sidewall with yellow, but in the heel, that stress is blue. And recall, we said that blue is either low tension or possibly compression. Now, this particular FEA is specific to the outside surface. I'm in agreement. The heel region is low tension, so I wouldn't expect breaks down in the heel, except there's another thing we have to consider. We didn't talk about it, so we'll do it now. The inside surface. If we got a cutaway of the inside surface here, and look at the stress levels at what we call the inside knuckle. Quite high, red. Consequently, we've got an area of high tension stress, and therefore we can get breaks there, specific to the inside surface, not the outside surface. Now, I don't know for a fact without looking at those samples that are being discussed here what's going on. So my suggestion is we'd actually like to do a fracture diagnosis. We'd like to look at how that break is coming about. And when we do that, we're going to find the fracture origin. And if I am correct in what I just mentioned, and you do have breaks in the heel, particularly if I get a circumferential fracture pattern bringing the entire bottom off, I'm probably going to have an inside knuckle origin where those stresses are high. Now, the inside knuckle is typically not touched, which means a stone, a seed, or embedded material is likely my origin source. Something to consider the next time you're going through that testing. We could analyze those samples and confirm that. All right, so that's the end of the Q&A. I hope you got your questions answered. If you got some more, bring them to us, and there's lots of ways to do that. But before we go, there is our next webinar that I've mentioned, Sand to Shelf. 6 sessions. They're going to be about 1.5 to 2 hour sessions each. We're going to be doing them starting September 1st. It's a Tuesday. We're going to do Tuesdays and Thursdays for 3 consecutive weeks. Very comprehensive, great seminar for anyone that needs to know a lot about the glass industry in a short fashion. Now, before you go away, remember to stay connected. You can add in LinkedIn as a way to be with us and see what's going on and what's coming up next. We've got posts going out several times a week. Things like this video with these question and answers are going to be found on LinkedIn. Don't forget about our newsletter that you can sign up quarterly, and you can do that by going to our website, americanglassresearch.com. So that is it for today. Thanks for joining me once again. I'm Bill Slusser, signing off from Studio 68.